Okay, good afternoon. So last class we discussed about different transposition ciphers, right? And today we move on to a topic called rotor machines, which is one of the breakthrough technology in cryptography history. So this rotor machine is an electromechanical device, okay, and it played a major role during your World War II. That's why we are discussing this one here. So Germans called these rotor machines under the name called Enigma, and Allied forces called them in the name of Hagelin, and Japanese had their own rotor machine named as Total. Okay. So it is a electromechanical device. That is, it will be having three cylinders which are being connected with each other. Each cylinder having 52 alphabets. I mean 26 alphabets for an input and 26 alphabets as an output. We can able to see this is a Hagelin rotor machine used by Allied forces during the World War II. Right. And here this shows a clear picture of how the connections are present inside this rotor machines. So you'll be having three rotors like 1, 2 and 3 or three gear kind of structure. Okay, all of them will have 26 input pins and 26 output pins, and these pins are internally connected to each other. Okay. So the combinations of connections will be known one and only with respect to the person who manufactured the rotor machine and to certain personalities. We will see how it works. This is only for your knowledge to understand. So the first diagram shows the initial setting of a rotor machine. Okay. We'll start off from this one, and assume this is your your first gear, second gear, and the third gear. Okay. These are the input pins. All the left hand sides are input and right hand sides are output. So in this, you can able to see the alphabets A, B, C, D up to Z is numbered starting from 24, 25, 26, then 1 to 23. Okay. Assume that now we are going to transfer a data called ABC. So in this, A is connected to 24, B is connected to 25, and C is connected to 26. Now what it will do, since this 24th pin is connected to 24th pin in the output here. Right. So A will be taken output here, and B will be taken as the position of 25, and C will be taken as the position of 26 here. Now these pins are connected to second rotors in different numbers. You can able to see 26 is connected to 7, 25 is connected to 22, and 24 is connected to 24. In this case, the key setting is such a way that here in this 24 itself, the both input and output pins are same. Right. Now in turn, okay, this 24 is connected to here 24. Right. 22 is connected to 22, and 7 is connected to 7 here. And the respective third gear, you can able to see 7 is connected to 20, 24 is connected to 18, and 22 is connected to 13. Now the output will be taken from the output pins of third gear. That is, you can able to see 13 is taken as I, 18 is taken as B, and 20 is taken as E. So if you trace the values, for example, if you take A is got start from 24. So if it came here, from here went to 18, and from 18 we got B. So if is transmitted A, B, C, A will be replaced with B, and B 25th pin from here came to 22. From 22 it moved to 13. So B will be replaced with I, right, and C will be replaced with E in this case. So this is after transmitting first transmission. Okay. So once this transmission is over, okay, you can able to see after a single keystroke, the entire keys have been moved on. That is 23 came here, 24, 25, and 26. Okay. 1 second. So 23, 24, 25, and 26. And you can able to see if you give the same input of A, B, C, Here you'll be getting different inputs, outputs as D, O, and Y. The same message, the same machine, but after a single keystroke, that is after first transmission, okay, here the entire thing changes. Right. So this is how a basic rotor machine works on. So anyone have any doubt in this one? So next we move on to a classification of cryptographic techniques under stream and block ciphers. I just want to give a brief idea about the stream and block ciphers because though it is not present in our module 1, we will be discussing based on these two things alone in the upcoming modules. So if you take all the cryptographic techniques from classical technique to the present day modern cryptographic techniques, we can able to divide these ciphers under two categories of called stream ciphers and block ciphers. Okay. If we see a stream cipher, okay, we can able to see an example here. Okay, when does I can able to call the particular cipher as a stream cipher? Suppose if you have a plain text which has the characters P1, P2 and P3 and goes on, and your cipher text or C1, C2, C3. So that is P1 is encrypted as C1 and P2 is encrypted as C2. For this encryption, I am not using a single key. That is to convert P1 to C1, I'll be using the key called K1. And to convert the plain text P2 to C2, I'll be using the key called K2 here. So here also there is a stream of keys. So each and every plain text is going to be converted into a cipher text using unique keywords present in the entire stream of keys. So that's why it is called as a stream cipher. That is, the encryption will be one-to-one mapping. That is, if you have a P here, this will be encrypted as S using the key called K1. L will be encrypted as O using a key called K2. Okay. This is how a stream cipher works out. Whereas if we go for a block cipher, like how we discussed about your Playfair cipher, your Hill cipher, these things come under block ciphers. That is, you'll be taking a block of symbols. At a time, you'll be taking 2 to 3 characters or more than 3 characters as a single block, and these block size will be always greater than 1. Okay, 1 second. Sorry, guys. So here your block size will have symbols which will be greater than 1. That is, each and every block will be having more than 1 character. So for example, here if you are plain text is a message which has to be encrypted, I created 3 blocks. Okay, each block has three characters: PLA, INT, EXT. Right. Value of M is 3 here. So here what will happen in sense, I'll take single block, that is I'll take block number 1 and I'll be encrypted using the key called K to get the cipher text with the block 1. And second block will be again encrypted separately here. And third block will be encrypted like this separately. Right. So this is a major difference between stream ciphers and block ciphers. Right. So anyone have any doubts in this block ciphers and stream ciphers? If it is clear, raise your hands. Okay, thank you guys. Thank you. Right. Then we have combinations. Combination sense, if you take modern day cryptographic techniques, you will be seeing that there will be a combination of both stream cipher as well as the block ciphers. I mean, both of them will be mingled together, not to make the system more robust. We'll be seeing such kind of cryptographic techniques in the upcoming modules. Okay. Now we move on to the final topic of your module one, which is called steganography. So here, steganography is an alternative to encryption. It is like a subset of cryptography. Here, what we are going to do in sense, we are going to hide the message. Okay, that is, it can be in terms of any format. For example, you can use invisible link, selected marking, pin punctures. These things will be used in a conventional books kind of thing, where you can able to hide a message. Then using a graphic image, you'll be using the least significant bit on a graphic message or in sound file. Sometimes even noise signals can also be used to transmit a message. Right. So here, I mean, if you have a noise here, noise means you'll be having multiple signals which have been placed. So in this, I'll be using one particular frequency to hide my particular message here. So major drawback of this steganography here is this: the high overhead when compared to the data. So how many of you heard of a term called overhead? If you have not heard of overhead, can you raise a hand? The term called overhead. Generally, if you what I mean by overhead instance, assume that you want to send a data of 100 bits, in general transmission. You go for any wireless transmission, anything. Okay. This 100 bits of data will be transmitted as a some 150 bits. The extra 50 bits, what it will do in the sense, this extra 50 bits are nothing but like it will be called as header files. This header file will be appended with your data. Okay. To successfully transmit this data, we need this support of this header file. This carry the information about your source address and other stuff, but it doesn't have any valid information for the receiver. So this header are nothing but all the bits which doesn't carry any information required for the receiver or transmitter are called overheads. So why here they are considering overheads are high in the sense, for example, if you are transmitting a message using your image or sound file, okay, your data may be 100 bits. To transmit this 100 bit, at least I need to send 2 MB size of image. Sound file sometimes it goes for 10 MB, like MP3 kind of things, right? So here your valid data will be in terms of 100 bits, whereas your overhead will be running in terms of MBs. Right? This is a major drawback in steganography. Right? So this is a basic thing in steganography. So with this, we'll conclude our module one. Okay. So before moving on to module two, this will be a homework. I have uploaded the PPT. So this is a steganographic message. If you people can able to find the message here, can you put the the hidden message in the chat box? In the meanwhile, I'll just open the second module slide. The chat box you can find, you can post a message. This is steganographic thing which is from a famous novel. Here and message is hidden here. So I want you people to find that message. Meanwhile, I'll just open the second module PPT. Anyone found it? Okay, let's be a homework for you people. In next class while coming, you just post me this message. Right. Okay, now we move on to second module. I hope the second module, I mean, the slide is visible. If it is visible, can you raise your hand? It is clear. Yeah, fine. Fine. So now we move on to the second module. One of the most important module among the 7 modules, because this module plays a major role to understand all other cryptographic techniques which we will be discussing in module 3, 4, and 5. Right. So I want everyone to listen to this module very carefully. Sorry guys, 1 second. So I want everyone to listen to this very carefully. Okay. So in this topic, I mean, in this module, we'll be discussing the following topics, starting from number theory and finite fields. Okay, as per the syllabus, it is, I mean, the principles of pseudo random generation is placed as a second topic, but generally we will go with the this one at the end. We'll move this to the end, right? Then we'll see these two theorems, which is a very basic theorem and a very important theorem also. Then Chinese remainder theorem. Then we move on to discrete logarithm and one of the most important topic called elliptic curve arithmetic, because it is a base for elliptic curve cryptography technique, which is used for both key exchange as well as for encryption purposes. Right. So start off with number theory and finite fields. In this, we will be discussing what do we mean by divisibility, division algorithm. Then there's an algorithm called Euclidean algorithm, which is a base for finding the multiplicative inverse value, which we discussed in our module 1. And this algorithm you people already studied, but you don't know that its name is Euclidean algorithm. You people already studied in your school days itself. Next, we move on to modular arithmetic, where we will be discussing all the modular operations, other steps. We already had a brief introduction and certain touch-ups in module 1, but here we will see it in a detailed manner. Then we move on to group, rings, and field. This is a very interesting topic, which is also a base for modern day cryptographic technique. Based on this, we'll be seeing finite fields of JF of P, then polynomial arithmetic, and finite field of different forms. Right. So generally, don't get panicked. These many topics, all are very, very small topics. We'll be running them very quickly. Right. So I think we can proceed, right? Yes. To start off with, we'll go with integer arithmetic. I'm starting from a school math. Okay. So first of all, what do we mean by set of integers? So in this module hereafter, whenever I say z, okay, z denotes set of integers starting from plus infinite to minus infinite. Does the set of integers include fractional values or decimal values? Yes or no? Whether a set of integers will have a decimal value in them or not? You can use the chat box to answer. Does the set of integers have decimal value or not? I think it's a very basic question. I think so. Yes, sir. I mean, integers will include decimal numbers also. Is there any other answer? No. Again, yes and no from Venkat.
Sir, only integers, sir. Floor values.
Okay, I mean, only integers means you're saying whole numbers, like only no decimal numbers you're saying, right?
Yes, sir.
Okay, that's the correct answer. Okay, now we move on to a topic called binary operations. So we can able to perform 3 binary operations over the set of integers. The 3 binary operations are addition, subtraction, and multiplication. Okay, so here I'll be taking 2 inputs here, and I can able to perform any operations of this one, and the output which I am going to get will also be a value which is present in the same set of integers. Okay. So can anyone tell why can't we place division under a binary operation? Why can't division come under binary operation? Any guess why only addition, subtraction and multiplication alone?
So it doesn't change the type of the outcome.
Doesn't change the type of.
These add, subtract, and multiply gives us the integer itself.
Okay, okay. You are saying that it won't. I mean, give a whole numbers. It will give. It will lead to some decimal values. You are saying, right?
Yes, sir.
Okay, okay. Any other answer? Any other answer? Okay, as Venkat also said the same thing. I think so. We can't get full values. Okay. Then any other answer? Okay, what people has said is correct, but in an easy way to say here the name denotes binary operation means okay, I'll be taking two inputs and I should get only one output of it. Whereas we go for division, I'll be getting two outputs. I won't get a single output. I'll be getting two outputs in the name of quotient and a remainder. So we can't able to place a division under this binary operation. What if people said this correct? We won't use a division in our cryptographic algorithm anywhere. We'll be sticking up with this binary operations alone. Right. So as I said, these are very basic things. That is, you can able to add, subtract all negative and non-negative elements to get the respective values. Now we move on to integer division. So integer division means if I take any two integers like a and n and divide a by n, we'll be getting two outputs called q and r, known as quotient and remainder. So if you want to represent them mathematically, I can able to write a is q times n plus r. That is, you are dividing a by n. If you divide a by n, you will be getting a quotient here and you will be getting a remainder here. So I can write a as q times n plus r. Right. So assume that if a is 255 and n is 11 and you are going to divide a by n, right? Here the value 23 is a quotient and this 2 is a remainder. Right? This is called a division algorithm. Now we move on to the exact part here. So what is the condition? Why is we are learning this basic spool math lessons? So whenever I say division, you'll be getting some quotient and a remainder. In division algorithm, there's a condition that a n will be a positive value always, the divisor, and the remainder should come out as a non-negative value. You should not get a negative value. Okay. Why we are stressing on this part, non-negative? Since from cryptographic point of view, as we already saw, whenever we get some minus value and if we take a modular operations, we want to push them into positive value. I hope you remember, right? The same thing, because whatever the value the A is going to take, A can take any negative value also. Okay. Your quotient, it's none of my business. I'm not going to bother at all about the quotient, but my remainder should come out as a non-negative value. For example, if you're getting your R and Q, suppose your remainder and quotient are negative, okay, will run for negative when your A is negative. So if you want to push my R to a positive value, okay, what we have to do in sense, you have to decrement the value of Q by 1 and if you and we have to add the value of N to R. This is what we people did during your conversion of a negative value into a positive value while we are doing modular operations. Since in modular operations we had a output based on remainder alone, we concentrate on this rule. Actually, if you have a quotient, you'll be dividing, sorry, yes, you'll be decrementing the quotient by 1. We'll see the same example. Okay, here you've taken A to be 255 and N to be 11. You got your quotient to be 23 and remainder to be 2, right? Suppose if I am taking minus 255, if you divide minus 255 by 11, I'll be getting my quotient to be minus 23 and remainder will come to minus 2. But my concern here is I should not have a negative value of remainder. So I have to convert this negative value into a non-negative value. So for converting this into a non-negative value, we have to use this rule. Decrement your value of q by 1. That is, you already got your value of q to be minus 23. Okay, decrement it by 1 so that I'll be getting minus 24. You got it here. And you have to add the value of n with r. This is n and this is your remainder, right? So 11 plus remainder is minus 2. You'll be getting the value of S9. Now if you solve this expression, minus 24 times 11 plus 9, your A will be the same value as minus 255. Right. So anyone have any doubt in this part? How to convert the remainder value, if it is negative value, into non-negative value? If it is clear, raise your hand. If you have any doubts, you can ask them. Thank you, Akhil. Anyone have any doubts apart from Akhil? No. This is a graphical representation of divisional equivalent. It's nothing much to discuss here. Now we go for divisibility part. So whenever I say any integer is divisible by another integer, then obviously what I mean in the sense the remainder will be 0. Okay, that is, we don't have any remainder. That's why you can able to write A as q time n if we are n is able to perfectly divide A. So why we are saying this in a sense? So in cryptography, whenever I represent a vertical line and n means the remainder is 0. That means A and n are perfectly divisible to each other. If I represent a vertical line which is crossed here and n means which denotes a and n are not perfectly divisible to each other. Right. So I can able to write like this one. If I write 4 a vertical line 32, 4 will divide 32 perfectly. Right. If suppose if I write 8 and this crossed symbol 42 means 8 can't divide this value perfectly. Okay, which will be giving us some remainder here. So what is the properties of this possibility, divisibility rule here in the sense, if A is perfectly divisible by 1, then obviously A will be always plus or minus 1, right? Second property, if A divides B perfectly and also B divides A perfectly, then A will be either equal to or minus, so it will be equal to plus or minus B. And comes the third property, if A divides B perfectly and B divides C perfectly, then obviously A will also divide, A will also divide C perfectly. This third property and fourth property will be widely used here. So the fourth property, if A divides B perfectly and again A divides C perfectly, then there exists a relationship. That is, A can also perfectly divide m times of B plus n times of C. The only condition is nothing but your m and n should be an integer value. So these are four properties you people have to remember with respect to divisibility is concerned. So able to see if you have a third property, so assume this is here A and B and B and C. So A divides B perfectly and B also divides C perfectly. Then I can able to say A will perfectly divide C also. So 3 will perfectly divide 45. Here comes the fourth property. This is A, this is B, this is again A, and this is C. So A divides B perfectly and A divides 9 perfectly. Now you can choose any values of m and n. Okay, so this is the value of m and this is the value of n. The only condition is nothing but m and n are integer values. Even you can go for negative values also. You can choose anything and you can able to check if you perform m times of 15, that is the value of p, and n times of c and add both of them, it will be a perfectly divisible value by a. In this case, you'll be running with 66. 15 into 2 will be getting 30, then 30 plus 36 will be getting 66. Right. Anyone have any doubt in this divisibility properties? You can raise your hand. If you have any doubts, you can ask. If it is clear, can you raise your hand now? At least if it is clear, then I will proceed. Thank you. Thank you. These are very simple things. Then, if you take any integer, like for example, integer 1, it has only one divisor. I hope everyone knows from school math. And any positive integer has at least two divisor, that is 1 and itself. They used to call them as a prime numbers, right? Now we move on to a next topic called GCD, greatest common divisor. We used to find this GCD, LCM, these stuffs in our school math, right? Why I'm again, sir, what is the use of learning these things again? These things form the base for our cryptography also. Okay, GCD. So what do you mean by GCD? GCD is nothing but a largest divisor which can able to divide the two integers equally, right? That is, it is common divisor of two positive integers, nothing but largest integer, it can divide both the integers. Right. So if you take a GCD of 60 and 24, it will go for 12. And if you take GCD of 2, 0, it is also 0. Right. Suppose if we take a GCD of two integers, these are two positive integers, and suppose it runs to 1. Okay. Then I can able to call these two integers to be relatively prime to each other. You can't say, sir, 8 is not a prime number, 15 is not a prime number. But if you take a GCD between these two, greatest common divisor, you will be ending up with the GCD to be 1. So whenever I get this condition, I can able to call these two integers to be relatively prime to each other. So these points to people should be very clear, because in modern day cryptography techniques, there are certain technique where you'll be dealing with integers, where you'll be asked to choose an integer which is relatively prime to other integer. So at that time, if I say relatively prime means, then the GCD between these two integers means it will go for 1. Okay, now we move on to school math. How will you find GCD of two integers when they are given to you? What is the method you will be using? You can use your chat box or you can unmute it. How will you find this GCD of two integers? Hope I am clear with my question, guys. How will you find a GCD of two integers? Your school math, basic school math. Got. Okay, I'll just show a method. Suppose, I hope you remember this one if I explain this to you. They ask you to find the greatest common divisor of two integers 25 and 60. So what I will do in the sense, I will take this 25 as value as R1 and this one as R2. So I have written this R1 and R2 and written them as 25 and 60. Always what we will do in the sense, R1 will divide this R2. It is a steadfast rule. So in the first case, 25 divided by 60. Obviously, we can't divide 25 by 60. So the quotient will be 0. So if I go with 25 divided by 60, I'll put quotient to be 0. So the remainder will be coming out as 25. Right. Next step, what I will do in sense, I'll push the value of R2 to become R1, and after the first iteration, I'm pushing this remainder value to R2. Next step, I'll be dividing this 60 by 25. So in this case, 25 will go 2 times, which gives me 50. So 2 times is a quotient. 60 minus 50 will get me a remainder as 10. Next step, I'm pushing this R2 again to R1 and the remainder is pushed here. So this is repeated until my R2 value becomes 0. Don't stop when your remainder becomes 0. This is where people make mistake. When remainders become 0, you should not stop. You go for one more iteration by pushing this remainder to R2, that by making R2 0, and this R2 is pushed to R1, and this final R1 value is nothing but GCD of the two integers. Assume here it is 25 and 60. Have you people did this same operation in your school days? Yes or no? Can you raise your hand? Yes, thank you all. You people did the same thing in your school days, and this method is called Euclidean algorithm. Nothing. Same GCD. Okay. Finding GCD of two integers using this method is called Euclidean algorithm. So what is the use of learning this Euclidean algorithm? Because why I am teaching this Euclidean algorithm in the sense, based on this Euclidean algorithm only, we are going to find the multiplicative inverse of any integer under any modulo operation. So anyone have any doubt in this GCD part? I mean, whatever I just said, it is expressed here in the zero code, and these are the facts of GCD. I mean, Euclidean algorithm. If you take a GCD of any integer and 0, the integer itself will come out as a GCD. And if you have a GCD of A, comma B equal to GCD of B, comma R, means then this R will be nothing but a remainder of dividing A by B. That is, if you divide A by B, you'll be getting some remainder, right? So your GCD of A, comma B will be equal to the GCD of B, comma R. These two facts people have to remember. So this is the basic of Euclidean algorithm. Anyone have any doubt in the Euclidean algorithm? You can ask me now. If it is clear, raise your hands. If you have any doubts, kindly ask me. Very simple, but you have to practice this one. Anyone have any doubt in the Euclidean algorithm? You can ask me. If it is clear, kindly raise your hands. Okay, thank you, Arun. Thank you, guys. Right. So if you go for higher numbers, you can able to see here. So I have added a few examples so that you can practice in your home and check. This is a very larger number. Don't really want to give you such kind of big numbers. So I want everyone to practice this Euclidean algorithm in your home. Okay. Because if you are clear with this Euclidean algorithm alone, you can able to learn the method called extended Euclidean algorithm. Okay. That's how this extended Euclidean algorithm works. You'll see now. So if you are given two integers, A and B, and we now can also find two other values called S and T in such a way that if you multiply S with A and if you add T times of B, you'll be getting the GCD value of A and B. That is, now we are going to find, generally if you go with Euclidean algorithm, you'll be finding a GCD of two integers. In extended Euclidean algorithm, you are going to find two more extra values of S and T. Okay, why we are finding this S and T, we'll see in the upcoming slides. Okay, so this S and T will be having a relationship with the GCD value like this. That is, if we multiply S with A and add T times with B, we will be getting the GCD value also exactly. We'll see how this works. This is the process. We already saw this is the Euclidean process. That is, you'll be taking R1, R2, remainder, pushing everything backwards. This is the steps for finding the value of S, and this is the steps for finding the value of T. So I want everyone to listen to this very carefully, because if you make a small mistake in this process, you'll be ending up with a totally different answer. This extended algorithm is a 10-mark question, right? That is, you'll be given the two integers, so I'll be substituting is R1 and R2 with A and B. Now, the first step of finding S is nothing but you initialize your S1. I'll be having two values of S1 and S2. First step, S1 will be always 1 and S2 will be always 0. And for finding the value of T, I'll be initializing the value of T1 to be 0 and value of T2 to be always 1. These are initial values. It is fixed value, that is S1 will always take 1 and S2 will always take 0 and T1 will always take 0 and T2 will always make 1. because this is where the initialization where you people make a mistake, right? So after this one, this process will continue to find the values of S and T. So as of now, in this slide, I want everyone to remember what will be the initial values of S1, S2, T1 and T2. Okay, now we move on to how we are going to find the values of this S and S1 and S and T, right? So in the first step, you will be getting a reminder here. At the same time, you will be parallelly processing here to find the value of S and T. We will see how this S and T has been found. This will be continued until you get your GCE value step. So once this step, you'll be getting some values for S1, S2, T1 and T2. So once you get your R1 value, when R2 is equal to 0, you'll be ending the process, right? Where you'll be choosing your R1 to be GCD of A and B. At that moment, you will take the S1 value and put and say it as a value of S, and you will take the T1 value and you will say the value of T1 as T. We will see an example so that we'll get a clear picture and okay, how this S and T are generated. So S is nothing but, I think I will directly go to example. Okay. S is nothing but S1 minus Q times S2. You'll be getting your quotients here, right? For each and every step. And T is nothing but T1 minus Q times T2. It is which you can able to see in here. S is nothing but S1 times S2 and T is T1 minus Q times T2. We will see a simple example so that you will get a clear picture here. Here they are given you, I want everyone to listen to this carefully. If you have any doubts, kindly stop me then and there. Okay. Here they are given you the two integers A and B to be 161 and 28, and they are asking you to find the GCD of A and B and the values of S and T. Right. So I am substituting R1 to be A, R2 to be B, and I initialize the values of S1 to be 1 and 0 and T1 to be 0 and 1. Now I am dividing 161 by 28. 5 times it goes, which gives me a remainder as 21. And I am computing this S. S is nothing but S1 minus Q times S2 in this first step. That is, I am just discussing this first step, right? In the first step, S1 minus Q times S2. S1 is 1, Q is minus 5, and S2 is 0. So I'll be getting the answer as 1. And T is nothing but T1 minus Q times T2. Here T1 is 0 and Q is 5 and your T2 value is 1. So I'll be getting the value as minus 5. The next step, I pushed the R2 value for R1, R value is pushed here, right? And here also the S2 is pushed to S1 and the S value is pushed to S2, the T2 value is pushed to T1 and the T value is pushed to minus T2. Next step, if I divide this 21 by 21, 28 by 21 goes 1 times, I'll get a remainder as 7. And in this case, if you want to find the value of S, you can able to see S is nothing but S1. So here S1 is 0 minus Q times S2 is 1. So I'll be getting minus 1. You can able to see the value of S here. Whereas in the part of T, right, part of T, you'll be going with the T1, which is 1, minus Q times, minus Q is 1, minus Q times T2 value is minus 5. So I'll be getting 1 plus 5, which gives me the answer as 6. Here we got the 6. And again, the next step, I got this 21 here, 7 here, 1, minus 1, minus 5 and 6. And I perform the same one. I got the value of remainder here as 0, which pushed it to this step to find the GCD as 7. Right. And here the value of S is minus 1 and the value of T is 6. So now if you want to cross check, as I said, we have S times of A plus T times of B will give me the GCD of A comma B. This is the theorem we just saw, right? So S is minus 1 times 161 plus T is 6 times 28, which is P. Can you people tell me the answer here? That is minus 161 plus 6 times 28. Can you tell me the answer in the chat box? Seven. Yeah, you'll be getting the value to be 7. This is the basic of external equivalent algorithm. Anyone have any doubt in this external equivalent algorithm? You can ask. If it is clear, kindly raise your hands. If you have any doubt in this external equivalent algorithm, kindly ask. If it is clear, raise your hands. Okay then. So with this we will wrap up today's session.